In this section, we're going to talk about the normal model, or also called the normal distribution. So the shape of the normal model looks just like this. It's our bell-shaped curve, or we could say it's normally distributed. So that's terminology you'll see come up. And with this bell shape, or this normal distribution, normally distributed, this is a common occurrence for data, meaning when we collect data, there's going to be some kind of expected value, something we expect to come through. It's usually what happens on average, which means when we collect data, that's where this peak is occurring. That's where we're getting the highest number of values. So if you imagine this as a dot plot, you can imagine all these dots in the middle there, and it's that they kind of focus around that middle there. So while most of them we expect to land right at this average or what we expect to come through, there's always going to be random variation. So we might have a little bit more, a little bit less, but still kind of high probability of occurring in this section right here. But then as we get further away from what's expected, as we go out to the right, which will represent larger values, and to the left, which will represent smaller values, the outcomes become less likely. So like being out here in this tail would represent having a value much larger than what was expected, and out here on the left-hand side, having something much smaller than what was expected. So in terms of probability, probability is going to link to the height of the curve. So the peak has the highest probability, and then being out in the tails where there's little height, that would be small probabilities. So with this bell-shaped curve, what we can do is calculate probabilities. Probabilities based on certain cutoff values, and finding is it a low probability or a high probability of occurring. Probability for this is represented as area under the curve. So with this normal model, whenever we're asked to find a probability with it, what we'll be calculating is area under the curve. And then what we'll also talk about is being given area under the curve, finding certain cutoff values. So we'll kind of do two sides of this. Now in this video, we're going to talk more intuitively about how these areas distribute, and that comes through with this piece that we'll talk about at the bottom here called the empirical rule. However, the empirical rule only works for very specific values. So in terms of wanting to find probability for any scenario that we want to, we're going to end up using GeoGebra. But in this video, we're going to stick with the empirical rule, and I'll show you how we could use it to get rough estimates of the probability and start to see the difference between high probable cases and low probable cases. But then from there, I'll show you where we get stuck and where we'll need to go into GeoGebra, which we'll look at in the next video. All right, so the famous bell-shaped curve, that comes through with this normal model. And this normal model is defined by two pieces. We need to know the center and spread. So when we have our bell-shaped curve, we need to define where is it centered, where's the middle of it, and how does it spread out. So we get an idea of the number line that we're working with. So the center of the curve, in terms of what value that is, that's going to come through as our middle number. It's the most probable case. And that'll be represented by a mean. And when we deal with these cases, we're going to have population data. So where the center is represented by mean, where the symbol we'll be using is mu for our population mean. So they'll describe to us what the population mean is. And then for spread, spread is going to come through as standard deviation, because those go hand in hand with each other, and it'll be a population standard deviation. Now that population standard deviation, that's going to help us make our number line, so that if we know where we're starting with the mean, then the standard deviation will tell us what numbers do we use for our number line, so we get an idea of the scale around our mean. Some notation you might see for defining the normal model, and this is similar to what we see for the binomial model. So we're going to have a random variable x, whatever that's representing for our case, and then we'd say is defined by, and if it's a normal model, we'll use capital N. So when you see that letter capital N in part of the definition of the model, it just means it's telling you the shape of the curve. We have a bell-shaped curve, and then they'll tell you two pieces of information. They'll tell you the mean and the standard deviation. So this notation's really nice and concise and can get you a picture for what you're working with, in that N tells you the shape. So that just means I could go and draw my picture like I did down here. The number that goes there for the mean will tell me where it's centered, and then standard deviation will give me a scale for my number line coming through. So let's see how that works in this case here. So we're going to look at the mean annual rainfall in Portland, and they're going to tell us it's unimodal and approximately symmetric, which that wording as well brings through bell shape, normally distributed, unimodal, and symmetric. All of those give us this same shape that I'm drawing down below there. So we have our bell-shaped curve, and then they're going to tell us about the mean and the standard deviation. So mean of 40, standard deviation of 8. So that wording right there, unimodal and approximately symmetric, mean of 40, standard deviation of 8, is all summarized in this notation right here, where X is representing the rainfall in Portland, N is telling me that we have a bell-shaped curve, 40 is telling me what the mean is, which is going to represent the center, and 8 is telling me the standard deviation, which is going to represent the spread. So with that notation right there, I can fill in the picture. So N tells me the shape to draw. Center of 40, what that lets me do, I'm going to clear out this graph a little bit so I have space, is that tells me what number goes right in the middle there for our number line. And then to fill in the other numbers, 8 tells me the scale to use. So it's like, what's the distance from here to that next mark? Well, we're using a distance of 8, and distance of 8, and distance of 8. And same thing below, distance of 8, distance of 8, distance of 8. So I can fill out my number line in that over here on this right hand side, 40, and then go up by 8, so that would be 48. Go up by 8 again, 56, up by 8 again, 64. And then same thing below, 40, but go down by 8, so 32, down by 8 again, 24, and down by 8 again, of 16. So the mean will tell you what the middle number is, and then what the standard deviation is tells you how to fill in the rest of the number line, using that as kind of your jumping distance for number to number. So you can imagine, like, say we had a very large standard deviation, that means our number line is going to go very far. So say this was, instead of 8, say it was 20. So we'd see 40, 60, 80, 100. We'd see a lot more numbers in the scale. But then as standard deviation shrinks down, we'll be more zoomed in around 40. So say we had a standard deviation of 1 here. So we'd have 40, 41, 42, 43. And then we'd have this number line that would be really small and close to 40, which makes sense because small standard deviation means little variation, so we'd be very close to where we expect to be, whereas large standard deviation means a lot of variability, so we could see a lot more possibilities. So with the wording of the problem, that's how you can get a picture to kind of visualize what are the likely outcomes and what are the unlikely outcomes. So I'll leave some of those up, but just to clear it out a bit, because now what we can do with our picture is see what are some likely outcomes. So the values that are close by, and thinking about like 1 standard deviation above, 1 standard deviation below, there's a high probability there. So if they have Portland rainfall and it was 34 inches one year, yeah, that's likely. I wouldn't have a problem if someone reported that. If Portland reported a rainfall of 70 inches, which isn't even on our number line here, it's out there somewhere, I would probably first say, ooh, check that data, something might have gone wrong. It's not impossible, but as we get onto the details here, they're just so unlikely that it could be just an outlier, it could be computation error. We want to be careful of those very low probability cases out in the tail there. So something we want to get to is this idea that probability is coming from area under the curve. So that's where I could say like 32 to 48 inches has a high probability because that covers a lot of area of the curve. Being out at like 56, 64, very low probability due to area under the curve. So some cases we're going to see come up, just to give you an idea of what we'll see, is it'll always be area. So maybe we'll look at area less than or equal to some number. So if we start to use less than or equal to, what we'll have is they'll tell us some cutoff. So say it was like 24. So we'd say we want to see what's the probability of being less than or equal to 24. So we'd have our cutoff value, and then what we would want to find is what's the area to the left to represent those lower values. If we want to find the probability of being larger than some number, what we would do then, so like more than or equal to some number, and actually let me fill in x less than or equal to some number, x larger than or equal to some number. In this case, we'd have some cutoff. And if we want the probability of having larger than that number, we take the area to the right. So probability of having that number even larger, and then probability between two values. So we'd have a lower bound and an upper bound, and what we would do is find the area between. Now, when we do get to GeoGebra, it's going to be very similar to what we did with binomial. We're going to see the same exact notation coming up, so it should feel familiar when we get to this. One difference, though, that we want to keep in mind, when we worked with binomial, we had these discrete cases. So something we talked about was like the difference between less than versus less than or equal to. So when it was like strictly less than, we had to adjust because it didn't quite work with the discrete cases. But now what we have, when we work with the normal model, we have a continuous number line. So if, say this was the case of less than or equal to 24, and I wanted to compare that to what would happen for x less than 24, it ends up being exactly the same, because the difference would be like cutoff of 24 in the area to the left, versus if it was just less than 24, being at 23.9999999 and less than, the difference in area there, it's nothing. It's basically zero. So a property that comes out with the normal model is our probabilities are based on area. So our limitation here is if we try to find the probability of x being exactly equal to some number, meaning if we have our bell-shaped curve and try to find the probability of an exact value, which would just be represented by a line on the graph, we can't do that. In this scenario, in this structure, that would have a probability of 0. So we always have to have this shaded area like we're seeing to the left here to find probability. We can't find probability of exact cases here. We'd have to use other tools of probability to do that. But a nice property with the normal model is that paying attention to that less than versus less than or equal to, or same thing with more than or equal to versus more than, it's the same. So we don't have to worry too much. As soon as they say less than or equal to, we work with it in the same manner. So with that set up, finding probabilities under the curve, what we're going to do is play around with this empirical rule. Now, something to keep in mind with this empirical rule is that it's estimations. Like with each of these probabilities we see come out, you'll see about there. So this is where we're going to use it very shortly, meaning we'll look at it, kind of get an idea of these probabilities, but then we'll improve on it by using GeoGebra to get the actual exact values. So something to think about is, say we didn't have numbers and we're just working with this normal model where we have a normal distribution with some mean and some standard deviation. So the mean always goes in the middle here, and then standard deviation notes our scale. So like to be 1 to the right here, that would be the mean plus 1 standard deviation. And then to be out here would be the mean plus, and that we go standard deviation and then another standard deviation. So that's where we move up by 2 standard deviations. And just to draw one more out here, the mean plus 3 standard deviations. So that's giving us our scale on the right-hand side. And then on the left-hand side, it's the same idea, but we're subtracting because we want lower values. So 1 standard deviation below, 2 standard deviations below, and then 3 standard deviations below. So what the empirical rule tells us is 68%, or rather about 68% of the data is within 1 standard deviation. So to be between those two values has about 68% chance. Then to be 2 standard deviations away, so to start at this value and find the probability of being between that lower bound and this upper bound of 2 standard deviations below and above, has about 95% chance of occurring. So very high likelihood of being within 2 standard deviations of that mean. And then our last one is to go 3 standard deviations below and above, has about 99.7% chance. So that gives a rough estimate of how probabilities centered around the mean behave. Now, with this, it gives us quick estimations of the probabilities that we're thinking of, and with that, it can give us an idea of when we're in GeoGebra, if we make an error, we can kind of get an idea of whether or not something went wrong. Now, something coming from this, like I mentioned, between 2 standard deviations has a 95% chance of occurring. So we have this rule that says anything outside of that is considered unusual or an outlier. Meaning, if you have something that lands 2 standard deviations or above versus 2 standard deviations below, anything out there is considered unusual. So we'll talk about that more, where we might see, is this value an outlier, and we'll just see how close is it to the mean. If it's within 2 standard deviations, it's a likely outcome, but if it lands outside of those 2 standard deviation cutoffs, it's considered unusual. And then to go out 3 standard deviations, extremely unusual, because there's only a 0.3% chance of being beyond that. So let's see how this rule applies. So we're going to use our same values that we just worked with. So still working with Portland rainfall. So let's say we were given that mean and standard deviation, and we want to find the probability of being between 32 and 48. So between those two values, this means we'll have 32 as a cutoff, 48 as a cutoff. And because we want to find, they said percentage, if same thing as probability in these cases. And so we want to find what's the area between those two values. And according to our empirical rule, because that's landing 1 standard deviation below and 1 standard deviation above, that is about 68%. So that's the best estimate we can get right now. So we could answer this question as about 68% chance of that occurring. For part B, what's the probability that the annual rainfall is more than 48 inches? So 48 was landing here. And if we want more than, and again, it doesn't matter if it says more than or equal to, we treat them exactly the same with the normal model. So we want to have more than 48, so we're going to start at 48. In fact, for notation, you'll even see me write the notation as, even though they're saying more than, I'm going to write more than or equal to 48 just because that's how it'll show up in GeoGebra. But a common mistake is to try to go 48.0001, but you don't have to do that here. So we would just use 48. Now this is a little different because the empirical rule tells us the probabilities between. However, with symmetry and that empirical rule, they can work together, meaning we said to be within 1 standard deviation had a 68% chance of occurring, and mathematically we'll work in decimals here. And in fact, GeoGebra will give you decimal answers, but we'll change to percentages. So mathematically, 0.68 in between, but we have symmetry here. So what that means is I could think about what's happening outside of that middle 68%. So if I go 1 minus 0.68, which what I'm using here is an important rule, and in fact I'll write it at the beginning here. The total area under the curve, you could think of that as our entire sample space. So if I wanted to know the probability of our sample space, which would be the total area under the curve, it's equal to 1. Meaning 100% of our data is under that curve, and we're just dividing up that 100%, or that value of 1, in decimal form. So what I'm using here is that if the total area is 100%, I'm taking out that middle 68%. So that would leave me with a 0.32, which that's giving me the area of the 2 tails together. There's 32% there. We have symmetry, so those 2 areas should be exactly the same. So to figure out just that single area, what I would want to do is cut that in half. So take that 0.32 and divide by 2 for a 0.16. So what I could do is fill in that picture of that over here's a 0.16 and over here's a 0.16, so I can see the symmetry of how those 2 tails are the same. And if you add up those 3 values, it adds up to exactly 1, or 100%. So this is telling me that there's about 16% chance. And now what we could start to see is how the areas compare. Like in the second example, the area is fairly small-ish. And over here, we highlighted a large portion of our picture. So with higher probabilities, you'll be shading more of the area, and with smaller probabilities, shading less of the area. Let's look at one more here with 24 inches or less. So 24 was out here at 2 standard deviations below. And if we want 24 inches or less, we want this teeny tiny area. So it can be nicest to draw a picture for these, because then I know I should be getting a small probability out. So we're landing 2 standard deviations below the mean, and the empirical rule says if we're 2 standard deviations away, that puts about 95% in the middle. So we could do is use the same rule that we just did in part B there of, well, we want a tail, so I need to think about what do I have left over when I take out that middle 95%. So I'd have this 5% left over, but that's the 2 tails combined. So to figure out what's in each tail, I need to cut that in half. So it'd be this 2.5% in each of the tails. And if you're unsure about it, just add them up and it should all add up to 1, and the tails should have the same area because we have this centered probability. So this would be about 2.5% chance. So now with this last one, I'm just going to fill in my number line a little bit here so we can see what's happening. So 48, 56, 32, 24. This is saying 54 inches or less. So now my value is landing in between here. 54 is somewhere in there between 48 and 56, and I want to find the probability of being below that number. Well, I can't use the empirical rule here because we're not landing exactly on a value that's a certain number of standard deviations away. So I'm stuck here. And this is just to show that the empirical rule only works for very specific cases. And it's very unlikely that it'll work out that you get to use it, because typically to land at those specific, however many 7 numbers that come through, very unlikely. It's more likely that we'll have these cases landing between the values. So this is where we can start to see the importance of, we need GeoGebra, or we need some sort of technology or program to help us find those other cases that don't specifically fit the empirical rule cases. So again, just to reiterate, empirical rule, it's great for getting a sense of how the probabilities distribute. However, our work from here on out, and when you do your homework, you'll rely on GeoGebra for finding all of these probabilities.